This video covers section 1.8 on higher order derivatives. This is the last section in chapter 1. So in this section, we're going to learn how to find the derivatives of higher order, meaning a second derivative, third derivative, etc. And then the application that we have for that is given a formula for distance, we should be able to find velocity and acceleration. Acceleration is an example of a higher order derivative. All right, so higher order derivatives basically mean you're going to be taking the derivative of a derivative. So if we have, say, the function f of x equals x to the fifth minus 3x to the fourth plus x, if I wanted to find f prime, or its first derivative, y prime or f prime of x would be by the power rule. The 5 would come down, so 5x, then this will become a fourth power, minus 4 would come down and multiply by the 3, giving me negative 12x, and then this will become a third power, plus, and then the coefficient of x here is 1. So the derivative function f prime can also be differentiated. So when we talk about a second derivative, it means taking the derivative of the first derivative. So we can think of the derivative of f prime as the rate of change of the slope of the tangent line. And it can also be regarded as the rate at which the derivative is changing. Remember that the first derivative is basically a slope, how fast the function is changing. So a higher order derivative is how fast the slope is changing, or how fast the derivative is changing. So we use this double prime notation for the derivative of f prime. So this f double prime, or second derivative, means take the derivative with respect to x of the first derivative. So we'll call f double prime the second derivative of f. So if we have this function x to the fifth minus 3x to the fourth plus x, its second derivative is found by taking the derivative of the first. So the first derivative was 5x to the fourth minus 12x to the third plus 1. So if I took the derivative of that, I would get 20x to the third minus 36x squared. And if I kept going for higher order derivatives, we use the notation f, and then this n in parentheses indicates we're not raising f to a power, we're taking that derivative of the function. So continuing, this would mean the third derivative of f would be the derivative of the second derivative, so 60x squared minus 72x. The fourth derivative would be the derivative of the third derivative, so 2 times 60, 120, x to the first minus 72. Fifth derivative is the derivative of the fourth derivative, so the derivative of this function is 120. And then I could keep going. The sixth derivative, then the derivative of this would be 0. And then from here on, in this particular case, no matter how high I go, right, any n value greater than or equal to 6, if I kept taking the derivative of 0, I just keep getting 0 every time after that. So that happens some polynomial functions. You eventually get to a 0, to which every derivative afterwards would all be 0. All right, so if we're using Leibniz notation for the second derivative of a function given by y equals f of x, we use this notation. F, and then this little power 2 of y, and then divided by or over d of x to the second power. Or that basically means the derivative with respect to x of the derivative of y with respect to x. So it's read the second derivative of y with respect to x. Those 2's are not exponents. It's just telling me to take a derivative twice. All right, so if I have this function, the first derivative, dy dx, would be 5x to the fourth minus 12x cubed plus 1. Then the second derivative would be 20x cubed minus 36x squared plus 0 by the power rule. Third derivative, 60x squared minus 72x by taking this function's derivative. Fourth derivative, 120x minus 72 by taking this function's derivative. And then the fifth derivative would be just 120. So we could use this notation to indicate the same things. Oops. All right, so let's try another example. For y equals 1 over x, let's find the second derivative. All right, so we can write that as x to the negative first. So the first derivative, dy dx, would be negative 1 would come down, x subtracting 1 from that exponent would give me negative 2. So negative 1 x to the negative 2. Then my second derivative would be taking the derivative of this. So bringing down the negative 2, giving me a positive 2x, and then to the negative third, because we're subtracting 1 here. And then I could rewrite that as the 2 over x cubed by moving my x term to the denominator to make the power positive. All right, here's another one. Y equals x squared plus 10x all to the 20th. Find both the first and the second derivative. So our first derivative requires the chain rule, the extended power rule. So by the extended chain rule, y prime, we would bring down the 20, using our outer function as the power first. So 20, leave this alone, x squared plus 10x to the power 19, times the derivative of the inside, which would be 2x plus 10. So that's how we use our extended power rule or the chain rule. All right, now to do our second derivative, we have to use the product rule. So the product rule, along with our extended chain rule, when we get to taking the derivative of that term. All right, so our first function, 20x squared plus 10x to the 19th, we leave that like it is, so that's the first function, times, this is our second function, so the derivative of the second function is 2, so times the 2, plus the second function, 2x plus 10, right here, times the derivative of the first. So that we're going to leave the 20 in front as the constant. We're going to bring down the 19, leave x squared plus 10x, make that the 18th power, and then the inside function's derivative again is the 2x plus 10. So this is our product rule. First function right here times the derivative of the second, plus this is the second function, and then all of this is the derivative of the first. All right, now we're going to clean it up. All right, so notice here we've got a 20 times a 2, that's 40. Over here, we have a 20, and then if I factored a 2 out of this set of parentheses, that would make that, if I took a 2 out and multiplied it by the 20, that would also be 40. Okay, so we're factoring out 40, because we got a 40 here, the 2 times 20. And then if I factor a 2 out here, multiplied by this 20, that's also a 40. We also have a common factor. We have an x squared plus 10x. This has a 19th power of that, and this term has an 18th power, so we can take that out, the 18th power. So if I took out 40, I got this, that's the 20 times the 2, so that's already been taken out, and then I took out 18 copies of this. So in this first term, there's only one copy of that x squared plus 10x left. So inside this bigger set of parentheses for the leftover, we've got that. From the second, all this stuff here is their second term. Remember, we took a 2 out of this and multiplied it by the 20 to get the 40 that we took out. So what's left here, if I took out that 2, is x plus 5. That 2 times the 20 was factored out. The 19 is still here. Remember, we took all of this out. That was the x squared plus 10x plus 18, and this is still left. Okay, so we're factoring out the common factor. All right, our next step is just cleaning up what's in here. There's nothing in front of this or applied to these parentheses. We can drop them. Here, they're just foiling x plus 5 times 2x plus 10 to get 2x squared plus 20x plus 50. Then inside of here, they have distributed the 19 through the parentheses to get this. And then finally, collecting like terms inside of here gives me this thing that we had factored out at the beginning, times this would then be 39x squared plus 390x plus 950. That's all the steps of the simplifying process. Sorry about the dog barking again. All right, so here we're going to do a couple more examples here on finding second derivative. So we're going to find the second derivative of all three of these functions. And then for this last one, we're going to find the fourth derivative. All right, so for the second derivative, we have to find the first derivative first, then we take the derivative of that to get our second. So for our first problem here, the first derivative would be negative 24x to the third plus 6x. And then that function's derivative would be negative 72x to the second plus 6. That's just power rule. Our second function here was 2 over x cubed. We're going to write that as 2 and then bring the x to the top as a negative third power. That's just rewriting the function. So then our first derivative using this form would be negative 6x to the negative fourth, which you could rewrite as this. And then our next derivative, I would just leave it like this if you don't have to simplify for MyMathLab, right? But from here, bringing that down then is 24x to the negative fifth. If that's your final answer, you probably do want to bring that power of x down to the bottom to make the power positive. All right, our next one, we start with our chain rules. We bring down the 2, leave this alone. That becomes a first power. That's the power rule. And then we multiply by the derivative of the inside, which is 6x. So that's our first derivative. Here we're just going to, instead of doing the product rule like we did before, here I'm just going to, since this power on this polynomial is a 1, we can just distribute the 6x and the 2 in here. So the 6x times 2 is 12x distributed here. So the 12x times 3 is 36x cubed, plus 12x times 1 is 12x. So that's just cleaning that up because it's simple to do. Now, if this thing had a power on it, like if this was higher than a second power like we saw before, and this had an exponent, that's probably not convenient because you have to FOIL and then distribute. In that case, you probably want to go ahead with the product rule like we did before. But here it's easier just to get to this point. Then we can take our second derivative from here. So 3 times 36 is 108, x to the second plus 12. All right, and then here we want the fourth derivative of 1 over x. All right, so the fourth derivative of 1 over x is the same as saying the fourth derivative of x to the negative 1. So that would mean if I took the derivative of this, we get negative 1x to the negative 2. So that would mean now I need the third derivative of that. All right, this function's derivative would be positive 2x to the negative 3. So now if I did that derivative, now I need the second derivative of that. This function's derivative is negative 6x to the negative 4. So that means if I took that derivative here, now I need a first derivative of that. So that derivative is 24x to the negative fifth, or 24 over x to the fifth. So basically you're doing it 4 times. Right, so that's the original function, that's the first derivative, then the second, then the third, and then finally the fourth. All right, our application here is using position to find velocity and acceleration. So the definition of the velocity of an object, that is s of t units from a starting point at time t, is given by. So this s of t function represents distance. So our taking the finding the velocity, meaning the rate of change with the slope, means taking the first derivative of your s function. This was our original definition. Okay, we're not going to use the limit definition. We're going to use our shortcuts, but basically that's the same thing. Right? So to find velocity, we're taking the first derivative of the distance or position function. And then to find acceleration, we'll call that function a. That's the derivative of the velocity. But remember, velocity is already a derivative of position, so basically to get acceleration, you're going to take the second derivative of position. All right, so say we have a position function or a distance function given to be s of t equals 10t squared. We want to find velocity at time t and acceleration. So what's the first and second derivative of s? And s is the distance from the starting point in miles, and t is in hours. Okay, then find the distance, velocity, and acceleration when t is 4. So after we found our velocity and acceleration functions, we're going to plug in 4. All right, so velocity is s prime. So if s is 10t squared, s prime is 20t. Acceleration is the derivative of the velocity. So the derivative of this function is 20. So the position value at 4 is 10 times 4 squared, or 160, plugging that into the s function that we were given. Velocity at time 4, velocity is 20t, so 20 times 4 is 80. Notice this is a rate of change, so this is just a distance, so it's just miles. Rate of change would be miles per hour. And then acceleration at time 4, plugging in 4 in here, that it's just a constant anyway, so it doesn't matter what t is, so that's just 20. But since you've taken a derivative, your unit changes. It's miles per hour squared. So miles for position, first derivative becomes miles per hour, second derivative, miles per hour squared. All right. A pebble is dropped from a hot air balloon. How far has it fallen, meaning distance? How fast is it falling, meaning velocity? And acceleration after 3.5 seconds. And let our position function or our distance function s of t be 16t squared. This time t is in seconds and s is in feet. That'll be important for units. All right, distance. It means just s of 3.5. The s is the distance function. So 16 times 3.5 squared, 16 times 12.25, or 196. And it says that our s is measured in feet. That would be our unit. Velocity is the derivative of position. So our position function is 16t squared. That means our velocity function is 32t. So find our function first. Then we're going to find velocity at the time they gave us, 3.5. So that's 32 times 3.5, or 112 feet per second, because time is in seconds. Acceleration, that's the second derivative of position, or the derivative of velocity. So the derivative of 32t is 32. So a of 3.5, plugging in the number they gave us, this is just 32, so it's 32 no matter what, but our unit is feet then per second squared. It's the same unit as velocity, only a second power on that denominator. All right, so our summary of section 1.8. The second derivative is the derivative of the first. In symbols, it's either f double prime or derivative with respect to x of f prime. The second derivative describes the rate of change of the rate of change. In other words, it's the rate of change of the first derivative. It's how fast the first derivative is changing, or how fast the slope of the tangent line is changing. A real-life example of second derivative is acceleration. So if s is the position function, velocity is the first derivative, describes speed or velocity. Any change in the speed is referred to as acceleration. So that's your second. So how fast the speed is changing is your acceleration. Common notation for nth derivative, any higher order derivative, is f with the derivative you're finding in parentheses to indicate it's a derivative and not an exponent of x. Or in Leibniz notation, the superscript on the top and the superscript on x on the bottom. Remember, they're not exponents, they're just indications of what derivative you want. So whatever the value of n is in this notation is the derivative that you're going to be finding of f. And that is the end of section 1.8, and that concludes the end of chapter 1.